Hello everyone, welcome to the video lecture on Python for circuit analysis and circuit visualization. The Google Colab notebook that I'm using here can be downloaded from the description below. The objective of this lecture is to show that Python can be used as a calculator or a tool to plot and calculate the response of RL circuit, RC circuit, and RLC circuit, as well as utilize the scheme.draw package of Python to draw electrical circuits. So the intention here is not to teach you details of Python programming, and neither is to teach you the um, basics of electrical circuits. So just utilize Python as a tool to do some calculations as well as then some general visualization of the circuits. So in this course, we'll look into RC and RL transient response. We'll also compare it to a multiple time constant. We'll also look into RLC oscillations, and then we'll look into some plots for the circuits. So the first line of code here, print hello circuits, just to show that if you have never used Python before, this is how you print something on Python. And to run this line of code, you either click on the play button here, or you can use Shift and Enter on your keyboard if you're using Windows. So I'll just click in here. The first time it takes some time, it says connecting, but once it's connected, it's pretty fast here. So yeah, so this tick mark means the line has been executed already and it prints hello circuits. So a few things, if you're not already familiar with variables, arithmetic exponentials, and importing libraries on Python, look into that. If you assign some values saying R is equals to 1000, here the R is resistance. So this is called as assigning a variable. Similarly, C is equals to 1 microfarad can be assigned as C is equals to 1 e to the power minus 6. So these two are the variables. We are dealing with R and C circuit. And arithmetic operation can just be done like this. So if you are looking into time constant, if you remember the time constant for the RC circuit is R times C. So we are doing that here. So we are assigning tau is equals to the product of R and C. So we are basically doing a arithmetic operation in Python. And if you want to print that results, you can just print it time constant is equals to tau in seconds. So I'll run this code and you'll see the time constant for this RC circuit would be 0.001 seconds. Okay, now let's look into um, some basic calculation. So let's assign the source voltage to be 5 volts here, and let's analyze the response of the system, RC system, at the time point of 0.002. So we basically put back in the response of the electrical circuits here. So if you don't remember what was the response of RC circuit, um, so for RC circuits, the capacitor voltage is given by product of Vs times e to the power minus t by tau. So the value of E is 2.718. So I'm just assigning it as arithmetic value, fixed constant, and then double asterisk means to the power of. So we print that as approximate capacitor value, and by running this line of code, and you'll get this capacitor voltage to be 0.67 volts. Now let's look into importing libraries as well as some exponential function. So import numpy is np, downloads the numpy package is, and we can do the operations starting with np. So again, the same values, R is 1000 ohm, C is 1 microfarad, your tau is given by product of R and C. Let's assume the source voltage is 5 volts, and we are looking for the response of the circuit to at the point time in 0.002 seconds. So the same equation, but then instead of manually typing in the value of E, which is 2.718, we are just doing NP dot exponential, which is basically it's e to the power. And this is the value on the e to the power. So same as above, just different way of doing it, more efficient way of doing it. But then the circuit response is not just one number. So it's a function of time. Whenever we switch the, whenever we change the switch, the capacitor either charges or discharges depending on the situation. And most of the time, we're actually interested in looking into the time response of the circuit. So on x-axis, we are always looking into time, and in the y-axis, we are looking for either the current or the voltage response of the circuit, depending on the type of the analysis we are going to do. So to do that, we are going to leverage the matplotlib, which is a Python library for plotting nice diagrams. So we are going to import NumPy again as NP. You don't need to do import NumPy in each block of cell, but just making sure that this block of cell is self-sufficient. But then you can just comment it out because we already did that in the earlier block of text. So you import matplotlib.pyplot as PLT. You have the same values as before, but then rather than giving a fixed time value of 0.002 seconds, we are assigning time in a range of 0 to 5 tau, and we are evaluating the value of VC at 500 different points between those two values. The reason the 5 tau is assigned should be obvious because the response of the RC circuits usually um, reach to the final value around 5t, 5 time constant 5 tau. That's why we're using 5 tau. You can use 6 or even higher. So then the same equation, the VC, the response of RC circuit is given by, so this is the equation for the RC discharging. So VC is given by product of Vs e to the power minus t by tau. Now we are executing this code, and then you'll see the exponential decay as we discussed in the class. So this is the RC discharging response. Okay. And sometimes we're also interested in looking into the output voltage at the time constant. So rather than plotting this as time, we are sometimes interested in looking it from the perspective of time constant. So what we can do is we can actually um, insert a vertical axis. So AXV line, it inserts a vertical axis uh, with the value of tau, which is 0.001 in this case, and we can assign a type of line we want as well as a label that. So if we run this line of code, it's basically the earlier code plus a vertical line. So the earlier plot uh, plus this vertical line, which is showing the one time constant. So if you look into this diagram, this value is around 1.84 and initial value was around 5. So we know that for the discharging case, the RC circuit discharges by about 63.2% of the initial value at one time constant. That is why at this point, the capacitor voltage is about 36.8% of initial voltage. Okay, so now that we are looking into discharging case, we can also look into charging case of the RC circuit. So everything remains same. The only change is here. So for the equation for the RC discharging was BC is equals to Vs times e to the power minus t by tau. But for discharging, it is Vs times 1 minus e to the power minus t by tau. And that basically subtracts everything. And then we get a reverse plot like this. So this is the plot here. Um, and if we compare that with the earlier case of discharging, this is the case of discharging. So you can um, run this code and see that. The reason I'm plotting this again is because the initial value is 10 volt. So just making sure I'm using 10 volt instead of the 5 volt that I was using earlier. And you can plot those two together in a single plot and see where's the response of charging versus discharging. So that should be clear. Let's next move to parameter exploration. So in this block of code, we'll look into how would the response of the circuit change if we change the values, such as what happens if we double the value of resistance, what happens if we have a capacitor with a smaller capacity, which response is faster, things like that. Those can be explored using the using a loop system. So this code is basically same as earlier case of charging. The only difference is rather than using one value of R, I am assigning three different values and storing it in this list. So 500 ohms, 1000 ohms, and 2000 ohms. And I'm looping through each of those resistance values stored and calculating tau, time, space, and the response we see at this point and plotting those all in the same equation. If we run this code, we can see that as the value of resistance starts decreasing, the response is faster. Um, and I would like you to do similar. So this block of code is exactly same as the above code, like this one. But what I want you to do here is rather than actually, so this one, so rather than actually changing the R values and looping through R values to see the effect of resistance on RC charging, I want you to have different values of capacitance and a fixed value of resistance. Let me do this back again. Um, so this was our initial code actually. So what I want you to do is change the values of C, maybe 3 or 4 different values of C, and have the R value as constant, maybe just single R value, and loop through the values of C here instead of R and see the effect of discharging, effect of capacitance on the RC charging. So go ahead, pause the video and change this line of code from here to here, um, also the title, and then come back after you are done. Okay, I'm assuming that you did that. Yeah, pause the video and went through that. So what I'm going to do here is change it. So instead of having a fixed capacitor, we are going to have fixed resistor, let's say 1000 ohms in this case. And rather than looping through the R values, in this exercise, we are going to loop through the C values. And a good C value here is this. So let's look into that. Um, So I'm going to have these 3 different values, maybe let's say 2, and maybe let's change to -7. And rather than looping through the R values now, I'm going to change these to C values. Tau is still RNC, so no need to change that. We are still looking into the 0 to time, 5 times time constant. So no need to change that. No need to change here. So the only thing we are going to change is we are actually looping through capacitance. So our level should also come as capacitance, not as a register. So, and then this is effect of capacitance. So now I can save it and run it. And you'll see the effect of capacitance or resistance. Similar, just the different values lead to different nature. So this one is with a e to the power -7. So this gives the fastest response. So that is how you can play around with the values and see the response of each of those variables on the effect of um, on the effect on the resistance. On the effect on the response of these circuits. So now we know how to use Python as a calculator to do some calculation. Next, let's move into circuit visualization. In this example, we'll look into like multiple different types of circuits, actually, not just RC circuit, although it says RC circuit. And to do that, SchemDraw is a package in Python that helps with that. So and that does not automatically comes in Google Colab. So if you're using Google Colab, you'll have to install this package. For that, you can just do pip install SchemDraw. And if you run it, it will probably take a minute or so. And then it will download it. Once it is downloaded, it will show that installation is successful, and then you can import the SchemDraw and you can import the elements as ELM of the SchemDraw. And now let's look into some actual drawing examples. So let's draw arch charging circuit. So this line of code actually, what it does is draws things in sequence. So it first draws the source, DC source 5 voltage, and we'll draw one resistance, 1 kilo ohm resistance, and then 1 microfarad capacitance, and then we'll finally add a ground. So similar to what you do with your hands, handwriting drawings, we draw one element at a time, and that is exactly how we are going to follow this code. So if I comment out all of these comments by clicking on control and forward slash, you can comment this out. And if you save that and run it, what it does, it doesn't do anything because there is nothing uh, to plot. So what we do is we start plotting one element at a time. So in this case, I am going to uncomment this, run this, and if you look into this, it draws a 5 volt DC source. and I need extra line, and I will add a register element on the right of that line. So if I uncomment these two sections and if I run it, see, I'm adding resistance. So that's basically how you draw different elements in scheme draw. So you add one element at a time. Um, the position and everything with the scheme draw has to use functions like this, which is not very efficient. So you'll have to play around and look into what works best. So it takes some practice and time to actually make good circuit drawing, uh, but it still gives some idea on how can you utilize this. So now final component is the earthing. So this you can see that I started from 5 volts, and this is the circuit. Um, so in this one, we actually hard coded the values of resistance and the source voltage and the capacitance on these each line of elements. But usually you don't want to do that because a lot of time we are actually drawing circuits which have basically the similar structure, but then we just change around the values. So it is always a good idea to store the variables first and then start drawing these circuit. So in this case, we are storing the source voltage, the resistance, and the capacitance, and actually drawing the circuit and automatically makes the figure. So same as before, the only difference is if we need to change any of those, we can just change at the top of the code without having to go through each line and change here, here, and here. Okay. Um, so, and you can also label the voltage across capacitor as VCT using extra line of code at the end of the um, section where we add the capacitor element in this scheme draw. Okay. But then a lot of times these circuits are repetitive and we want to actually make a function that we can call into. So let's wrap everything around a function. So we define draw RC circuit and we give a random initial number, default numbers as shown here. And we make this function. So when I run this function, it does not display anything because we are defining a circuit, but we are not actually calling the circuit. So if you want to actually draw this, you'll have to call the circuit by calling draw RC circuit. And if you don't provide anything in between the parentheses, it basically uses the same values as the default values mentioned here, and it will plot your circuit. So this one is the default values that were assigned here, 5 volt, 1 kilo ohm, and 1 farad. But if you want to reuse the code again, but with the different values, so what you can do is you can call the draw RC circuit, but then we use different parameters in the circuit, and then we run it, we get the same figures, but with different parameter values. And you can do similarly for RAL circuit or RLC circuit. In this case, we are doing a similar approach for RAL circuit. So we are having a source voltage, default source voltage of 10 volts, default resistance of 100 ohms, and a default inductor of 50 millihenry. And if you run this line of code, you'll get nothing because it just defines the circuit. But if you really want to see that, you'll have to call the function draw RL circuit, and it will draw a circuit with the default values of 10 volts, 100 ohms, and 50 millihenry that we defined here. Okay. But if you want to change again, similar to the earlier approach, you can just change the values in the parentheses and you'll get a different circuit. Okay, let's draw a few more circuits. So in this case, we are defining a function to draw a series RLC circuit, and we are basically adding a source voltage, a resistor, an inductor, a capacitor. We are also showing the label of the capacitor as VCT, the voltage across that line, and we are closing the loop and adding a ground there. So if we run that, it defines the function, but then actually to show or visualize the circuit, we have to call the function draw series RLC, and that will do the job. Okay. Um, Similarly, we can draw parallel RLC circuit using scheme draw. So if you run this line of code, actually I'm adding the call function directly in this line of code, so it will actually plot the circuit here. So this is RLC circuit. Okay. Um, Now we know how to draw a circuit. Now we know how to do basic analysis. Let's move into actually doing a circuit analysis of parallel RLC circuit in Python. So This one will analyze this equation, but then we first need to define circuit equations. So we'll do a derivation, and then we'll actually look into the response of the parallel RLC circuit. So in this line of code, we are importing NumPy for calculations. We are importing matplotlib for the plots, and then we are actually importing SciPy and importing the solve IBP for the initial value problems. So because now we're going to deal with differential equations, um, we need to import these packages for the analysis. So once you run this code, those packages are installed, and now we're looking into general parallel RLC form where there is a source, the resistance, inductor, and capacitance. And to derive the equations necessary, what we can do is, since those elements are in parallel, we apply KCL at this top node. So the current coming from this source actually divides between resistor, inductor, and capacitor, and we apply KCL as top node to get the source current is divided across those three elements. And from the current voltage relationship, we know that the current across resistance is related to the voltage as V by R. The capacitor current is related to the voltage as C dV by dt, and inductor voltage related to inductor current as L di by dt. And if we substitute these relations back in this equation, we'll get something like that. And if we do take a derivative with respect to time on that equation, and use the inductor relationship, which is Vt is equals to L di by dt, we get a second order differential equation shown here. Okay, but for the circuit visualization, we usually use first order system rather than the second order system. So what we do is um, we use what is called a state space form for numerical simulation. But before that, you can also look into the response of this second order system. So if you compare this equation with the standard second order equation form, you'll get values alpha is equals to 1 divided by 2 RC and omega naught is equals to 1 divided by root under LC. The alpha is a damping factor and omega naught is the resonant frequency. And if your value of damping factor is less than the resonant frequency, you get a response which is underdamped. If your alpha is greater than omega naught, you get a response which is overdamped. And if they're equal, you get a response what is called as critically damped circuit. Okay, but for Python, it is a lot easier if we actually write those equations, second order differential equation into two first order systems. So we can reuse the initial formula from KCL here, and we can rearrange in terms of voltage. And from inductor law, we can actually have two first order system instead of one second order system to solve those equations. So dV by dt is 1 by C, the IST minus V by R minus IL, and dIL by dt is equals to V by L. So these are two required equations to solve the second order equation that we derived here. Okay, though those two equations can actually fulfill that. And we'll do that using Python next. So we already ran this line of code above, so we don't need to do that. But then let's look into example. Um, let's define the variables. So we are assigning R as 1000 ohms, L is 0.01 henries, and C is 1 microfarad. And you can just print that by running this code and you'll see the output. And let's calculate these equations. So alpha and omega naught, and see if the response is underdamped, critically damped, or overdamped. Okay, so your alpha is 1 divided by 2 RC, and omega naught is 1 by square root of LC. So this line, of course, is basically doing that. So it is assigning alpha is equals to 1 divided by 2 RC, and omega naught uh, is 1 divided by square root of LC. So NP to the square root takes care of the square root. And if we can print alpha and omega calculated from there, and we compare those two values, if alpha is less than omega naught, the response is underdamped. If alpha is equals to omega naught, that is critically damped. So we use is close because sometimes those calculations round up and they're not exactly same, but they're very um, very near to each other. So that is why we use is close instead of equals to. And then finally, if those cases do not satisfy, the final response will be overdamped. So in this case, if we run this line of code, we'll see that your alpha value is 500. Actually, this is wrong because the damping factor is measured in Nappers per second, not in radian per second. So that is something you need to understand from electrical circuits perspective. So anyways, those values are 500 and 10,000, but then our alpha is way less than omega naught. That means the response is underdamped. Okay. Um, that response in the equation above, if we set the source current to zero, the response is then determined fully by the initial story that is initial energy that is stored in the system. So in that case, it is called as natural response. So in that case, we also need to find the initial values of the circuit. So the initial values can be, sorry, wait me for a second. Sorry about the interruption. So in this example, we'll use initial value of voltage as 5 volts and the initial inductor current as 0 ampere. If you are wondering how can we get this initial value, please refer to my other videos posted in this playlist. They go through the circuit analysis in detail. So once we have those, we define a function called as parallel RLC ordinary differential equation, where we need the inputs, time. The X is basically the voltage and current, capacitor voltage, inductor current that we need based on these two equations. So we need the values, right? So we are using those, and then we need the values of R, L, and C, and the type of the function, the source function. So V and IL are the values of X. So we assign that here, and we basically provide the equations. So dV by dt and dIL by dt. So those two equations, those are our governing equations. So we're just basically rewriting those equations here on the function, and we are returning those two functions. And then we are looking if the response to natural or not. So we define each natural, and if it's true, it's just returns 0. And this block of code actually simulates the natural response with initially charged capacitor. So the charged capacitor has a voltage of V naught is equals to 5 volts, the inductor current 0. And that is why our X naught becomes V naught, IL naught. So this is the situation right here. Okay. And then we specify a time range. Um, we start at 0 and we end at 0.001 second, and we can divide that time range between number of points that we want to evaluate. So in this case, we are starting from t start to t end, and we are actually evaluating in 2000 time points. And then we actually solve the natural response. Is solve natural is equals to solve IVP, initial value problem, where we provide the function, which is the parallel RLC that we defined here, and we evaluate that for the start time to end time. Our initial values are given by x naught, which are these equations. So 5 volts and 0 ampere. Um, and then we evaluate for the t eval for this range of time. And our arguments are RLC and is natural. Okay. If we do that, we define a function and sorry, RLC. So I need to run this line of code. Um, and then we can so it's storing all the value, but it's not showing anything. So to plot that, we need to plot the natural response voltage using matplot libraries pyplot. So we are using we installed a pyplot as PLT, so we're going to use that, and we are plotting time as x-axis and voltage as y-axis, and this is the natural response, right? So if we do that, you can see that the natural response looks like oscillating, but at the same time, the peaks are actually decreasing. So here peak is around here and then is around here. So that is under damped response. And we know that because the circuit we actually are using is under damped. So based on the calculation of alpha and omega naught. Okay. So that matches our response. We can also use we can also plot the inductor current response. So if we run the same line of code, now we can see the response in terms of inductor current over time. The only thing that is different between this block of code and this block of code is this. So solve natural gives us these current and voltage values, both values. The first value is assigned as V naught. So the first value will be voltage and the second value will be current. based on this equation, right? So voltage and current. So that is why when we call zero, which is the first sequence, first number in the sequence, it calls for voltage. So that is why we get voltage, and here we are calling one instead of zero. So that is the only difference between these two lines of code. So first one is node voltage, second one is inductor current. We can also look into force response with a step current source. So rather than saying that we don't have any source and just looking into natural response, we can look into step response. The only difference with the step response is it's basically similar to natural response, but that comes with addition of this first component, the final value of these, um, the force response. So now we are going to define I naught as 5 milliampere, and we're going to define a function is step. If it's a step function, then it gives us the value of I naught as some step value, which is 5 milliamperes. Uh, Otherwise, it gives us a value of zero. So that is basically what the if else um, loop is doing here. So if I run this code, doesn't do anything, just defining a function. And for the source initial condition, we can define the step response. It's x not a step, and we are actually assigning only values of zero. Um, that means the first one is voltage, second one is current. Just remember that. So the value of zero means the voltage is zero, which implies the capacitor is completely discharged. And the current of zero means that there is no current flowing through the inductor. Okay. And we are going to use similar equation, solve step response, solve IBP, parallel RLC ODE, still using the same ODE. Um, Now our function is x naught step instead of x naught natural that we used before, and an argument we supply each step. So same equation. Um, and if you run this, again, it does not plot anything because we need to call matplotlib and plot from there. So let's plot this and see the response. Okay. So we know the circuit is under damped circuit, so we still get the response like this, right? Um, and if we plot the current, so the voltage here is same as before, right? So it starts from it oscillates around the value of 0 volts. But if you look into current, right? So initially it was oscillating around zero, but now it is actually oscillating around 0.005, which is 5 milliamperes. So that is the response change. So in step response is basically combination of the final component plus the initial response. So initial response was oscillating around zero. Now it is oscillating around 5 milliampere. So it just moved by that factor. So yeah, so that was basically plotting. We can actually look into the effect of different values of resistance, inductor and capacitance into the response. So we know from the lecture that the capacitor registers certain change in voltage, inductor registers certain changes in current, and the resistor is the component that is dissipating the energy and provides the damping for the circuit. If the damping is weak, the energy exchange between the capacitor and inductor produce oscillations, and if its damping is too strong, the oscillation is reduced or removed. So let's look into the effect of resistance values on this response by running this line of code, and you can see that the oscillating response of the circuit changes with change in the value of resistance. Okay, so yeah, so to summarize, in this notebook, we looked into KCL, looking into parallel RLC circuit. We derived the second order governing equation. We expressed the circuit in state space form, which is basically using two first order system rather than one second order system to get the response. And we simulated both the natural and force component and observed how damping depends on component values. And before that, we also looked into how we can do basic calculations as well as draw different types of circuits using scheme draw package. So that's all for today. Thank you everyone for listening. Hope you guys enjoyed this video.